Okay, let's call this optimization part 2. Again, dealing with maximizing or minimizing. This part, as opposed to part 1, will be more theoretical or abstract in nature. If you're an SL student, it's probably more at the level 6, level 7 of SL, probably more appropriate overall for higher level students. Again, we'll take a paper 1 and paper 2 approach as we go through. So, two examples. Here's the first one. Consider the concave down parabola y equals 12 minus x squared, and the point A in the Cartesian plane right here at 0, 4. So there's 2 points, B1 and B2, such that this point A is as close as possible to both of those points. So if you kind of consider the spread of points on the parabola in terms of the distance from A out to these points B, there are 2 points where you can actually minimize that distance. And so if those points can be written in that form that you see here, respectively in terms of x and y, let's find P and Q. So basically, the heart and soul of this kind of analysis, because we're talking about actually minimizing a length or minimizing a distance, you've got in your formula booklet the distance formula. And if you consider that there's just some random sort of x, y values on here, and let's just think of those values that abstractly as x comma y, where of course the y values are always equal to 12 minus x squared. So you can actually think about what I'm calling b sub n, namely b sub 1 and b sub 2, will be the ones that interest us the most in terms of the distance from, if you will, that point to that fixed point being minimized. And so that's the basis for getting things started. So you've got the difference between the x's squared plus the difference between the y's squared. Of course, that's a fixed y value, and here's, the y equals 12 minus x squared representing those y values. So you end up getting what ends up being a distance formula that's a function of x. And so it might be better to write it as a function of x. And all I've done is just simplify things a little bit, done some expanding, which of course was not a requirement, but it might be a decent way to go about what we're being confronted with, which will be eventually a paper 1 derivative and minimizing the actual value of it. So here it is, the radical form in exponential form, and if we want to actually take the derivative, classic chain rule, 1/2 of that value, subtracting 1 times the derivative of the piece inside. And of course, if we're going to take a paper 1 approach, we'll just set all of it equal to 0. Interesting here, in spite of how daunting this whole structure looks, when you think about this b raised to the minus nth power coming down where it belongs in the denom, if you'll notice that I've taken 1/2 of each of these values to account for what you see here. What minimizes this derivative in terms of setting it equal to 0, really the only action would be the numerator, is what zeroes out this overall fraction, because the denom does not contribute to that. So you're really just looking at where that numerator is equal to 0, and when you factor out the x and take a look at what's left over and play it through, it looks like x is equal to plus or minus the root of 15 over 2. And so in terms of the actual form that we were looking for, which was a p, the root of p over 2 form, we pick up the p of 15, and knowing of course that y is equal to 12 minus x squared, we can actually plug that x value in and establish that the y value is 9 over 2, so q ends up being 9, because of course the form that you were actually looking for was that particular form there. That's what explains why p and q, the way they look, the actual values of 15 and 9 respectively. Okay, a second one talks about an inscribed rectangle within a semicircle. And so scales off a little bit here in terms of what you see, but this is sort of the top part of a circle. It just looks a little bit more involved because of the nature of the scale being a little bit different. So we're talking about a -3 out to 3. So we have something like here's 1, 2, 3, right? So in terms of the scale, and different scale on the y-axis as well. So what we want to do is actually find the dimensions of this actual rectangle that can be written in this form here. Here's your longer side, so some a root b form by a root b halved. That's a smaller side, all right? So a comment here about, because I've used the GDC instead of some better technology, and so when this kind of thing shows up, that really is just what I call cheap technology, because there are some resolution issues, and of course that really should be completed as the top part of a so-called semicircle. I'm going to call this value here x, and you have some choice there in terms of actually labeling. You could call the whole side x and call this y, but I'm going to call this x, which makes the whole length here 2x, all right? So that's pretty clearly described to you here. You can have a read. And so the overall area of this rectangle is going to be just its length, which in this case will be 2x times y. And so that area, in terms of us having a play with that, is something that's currently a function of two variables, and we actually want to somehow find that typical bridge between x and y to kick out, in this case, the y value and bring back y as a function of x so that we can actually have the area as a function of or dependent upon one variable, which actually looks like that. So more formally, so we're trying to get an area function, which we are actually trying to, in this case, in terms of what the actual question is, we want to actually find the largest possible area. So we're interested in maximizing that area. So I thought I would throw this into the GDC for starters. So here is the actual function that's being graphed, and of course has some kind of a maximum value at around 2.12ish. And the y value, of course, to remind you, is the y value of the actual function and not the y value necessarily that we're looking for in terms of this y value here that creates the length, because there's the usual three variables in play, x, y, and in this case, y standing for the actual area. So let's pick up as if this is a paper 1. So let's actually take a look at this function here. We need to differentiate it and set it equal to 0. And so that requires a product rule as well as a chain rule within the product rule. So here's first times derivative of second, right? Which will be swinging this down, repeat minus 1 times the derivative of the piece inside. So all that is first times derivative of second plus second, this piece here, times the derivative of just the first, which will be 2. And so if you look carefully and have a go at trying to simplify all of this, you should be able to pretty quickly, hopefully, come up with what you see here. And setting this, once again, in a paper 1 fashion equal to 0 implies all of this, for as, again, daunting as this looks, has to be equal to 0. I decided to sort of treat this the way it is and just bring this guy down. And then if you multiply both sides by this denominator, so this times itself is what's giving you 9 minus x squared raised to the first. And of course, this denominator, when multiplied against this term, just cancels it out. And of course, this times 0 is still 0. So you get something here that's actually pretty reasonable. And solving for this, not too daunting. Don't forget your plus or minus when it comes to what we're trying to do here, with at least considering for starters that there's a negative value as well. However, we have clearly defined x to be this positive length here, and we're trying to strive, of course, for a form that looks like this. And so if you start to have a further think about that, so we need the x being 3 over root 2, and then I rationalized that, and then the doubling of that x value actually gives you, because the denominator, you lose that, ends up being 3 root 2. And so that's going to be the longer side. That's the a value. And the b value that we need in terms of some a root b form. And then plugging that into this relationship here to get the actual y value, you can actually determine that it's 3 root 2 over 2. Okay? That was kind of fast and furious. You can listen to it maybe a couple more times, but that's pretty much it. Okay, thank you.